Welcome to the NESC unit on sample rate and Nyquist frequency for data acquisition and telemetry systems. This unit contains some MATLAB exercises, and you are welcome to stop or pause this presentation at any time in order to complete the exercises. This presentation is sponsored by the NASA Engineering and Safety Center, NESC Academy, and by Dynamic Concepts Incorporated of Huntsville, Alabama. My name is Tom Irvine, and I am the instructor for this unit, and you're welcome to send me an email or give me a phone call if you have any questions. Thank you. Engineers collect accelerometer data in a variety of settings, and the examples include aerospace vehicle flight data. This could be from launch vehicles, helicopters, or aircraft. Automotive proving grounds, machinery condition monitoring, building response to seismic excitation or even to wind loading, and also modal testing of structures. So in order to set up a data acquisition system, we need to establish a sample rate. This is a very important parameter. And we'll be discussing the sample rate in this unit, as well as a few related topics such as the amplitude resolution. The accelerometer is the transducer which measures the data in analog form, and this could be vibration data or shock data. The analog signal is then sent through a signal conditioner, and the signal conditioner may have an analog low-pass filter, and filtering will be covered more extensively in Unit 18. An understanding of the sample rate criteria requires some preliminary consideration of filtering, however. Now, low-pass filtering of the analog signal is necessary in order to prevent an error source called aliasing. And later in this unit, we'll be looking at a slide which shows a graph of the aliasing error effect for a sine wave. And aliasing is considered more thoroughly in Unit 17. But one example of aliasing that you may be familiar with is, for example, if you've ever seen an old Western movie on TV, and if you've ever watched the stagecoach going quickly down a road, you may see that the wheels appear to spin backwards, and that's an example of optical aliasing. And the same type of problems can come up in our vibration and shock data as well. So we really need to be careful about the sample rate, and it's very important that we apply an analog low-pass filter to the data prior to digitization. And we'll be discussing recommendations for setting the sample rate and the low-pass filter frequency in this unit and in the next unit. We're going to be setting two requirements for selecting our sample rate for our data acquisition or telemetry system. The first requirement is that the sample rate must be greater than the maximum analysis frequency. And the industry guidelines are shown in this table. So let's consider that we have a frequency domain analysis. This could be a Fourier transform or a power spectral density. Now in this case, our minimum sample rate must be greater than twice the maximum analysis frequency. So for example, if we have a power spectral density that we need to analyze up to 2000 Hertz, then our sample rate should be at least 4,000 samples per second. Now for a time domain calculation, our sample rate should be greater than 10 times the maximum analysis frequency. Now an example of a time domain calculation would be a modal transient analysis, and this includes a shock response spectrum calculation. The frequency domain requirement in the previous table is based on the fact that at least 2 time domain coordinates per cycle are required to resolve a sine wave for analytical purposes. In other words, for our highest frequency of interest, we need at least 2 points to characterize the corresponding sine function. Now the Nyquist frequency is equal to 1/2 the sample rate. The frequency domain analysis thus extends up to the Nyquist frequency. So for example, if we need our power spectral density to extend up to 2000 Hertz, then we should sample the data at a rate of at least 4,000 samples per second. Then we would represent the power spectral density up to 1/2 the sample rate, which is the Nyquist frequency, which is 2,000 Hertz. And note that some conservative sources specify a value of n equals 2.5 for frequency domain analysis. So if we need our power spectral density to be up to 2,000 Hertz, then our sample rate should be 5,000 samples per second, per the more conservative rule of thumb. An excellent reference for these guidelines is the Handbook for Dynamic Data Acquisition and Analysis, which is published by the Institute of Environmental Sciences in Illinois, and you can order this document by going to www.iest.org, and I highly recommend it. And here is a shock response spectrum from a pyrotechnic shock event. And this is from actual flight accelerometer data from a suborbital launch vehicle, and it was for the stage 2, stage 3 separation. Now the x-axis is the natural frequency in Hertz, and the y-axis is the peak acceleration in g. And the shock response spectrum, or SRS, is calculated in the time domain. It's a modal transient analysis. And pyrotechnic shock is typically analyzed up to 10,000 Hertz, or 10 kilohertz. So our sample rate must be at least 100,000 samples per second in order to satisfy the rule of thumb that we established on a previous slide. And note that sometimes we characterize the sample rate in terms of the equivalent frequency in Hertz. So 100,000 samples per second is equivalent to 100 kilohertz. So let's consider the spring mass system that would have a natural frequency of 10,000 Hertz. That system needs at least 10 points in order to characterize its response. And that is what drives the requirement that our sample rate be at least 100 kilohertz, or 100,000 samples per second. Now here's a simple diagram showing how the aliasing error may occur. So in this plot we have a time history. The x-axis is time in seconds, and the y-axis is some amplitude metric. Now the red curve is a sine function, and that is the actual vibration event. Now the data is going to be digitized, but the sample rate will be inadequate in that the sample rate is too low. So imagine that our data acquisition system digitizes the data such that it is represented by the 4 blue dots. Now consider that the digitized data is to be processed by a Fourier transform program. The software algorithm will effectively take those 4 blue dots and do a curve fit of a sine function through those dots. So what is now happening is that this higher frequency energy is going to be represented by a lower frequency sine function. And this is clearly an error from the resulting distortion. So our second requirement is that the sample rate must be greater than the maximum frequency present in the source energy at the measurement location. And this requirement is necessary to prevent the aliasing error. And this requirement is also independent from our previous requirement, which was based on the maximum frequency of interest. So let's consider that we have a frequency domain function such as a Fourier transform or power spectral density. The minimum sample rate for this case must be greater than twice the maximum frequency in the source energy. Then for a time domain calculation, such as a shock response spectrum, the minimum sample rate must be greater than 10 times the maximum frequency in the source energy. Now Shannon's sampling theorem states that a sampled time signal must not contain components at frequencies above the Nyquist frequency, and again the Nyquist frequency is equal to 1/2 the sample rate. And Shannon's theorem applies to frequency domain analysis. Well, here's the challenge that we face. How do we know what the maximum frequency will be for our source energy? And in many cases, we simply do not know. So here's the solution. We must pass our analog data through an analog low-pass filter. And this must be prior to digitization, because once we've digitized the data, it's too late to prevent the aliasing error from occurring. Now, the frequency and type of filter that should be used will be covered in the upcoming units 17 and 18. Here's a summary of our two rules of thumb. The first one is that our minimum sample rate must be greater than n times the maximum analysis frequency. Then our second requirement is that the minimum sample rate must be greater than m times the maximum frequency present in the source energy. Now, for a frequency domain analysis, both n and m are equal to 2, and for a time domain analysis, both n and m are equal to 10. And it's important that we meet both requirements. And note that these two requirements are usually independent. Now let's apply these two rules to a test situation. So an accelerometer must be mounted on a rocket engine for a static fire test. The resulting vibration data will be transformed into power spectral density curves with an upper frequency of 2000 Hz. The highest energy component in the data is expected to be 5000 Hz, however. So what is the minimum sample rate per the guidelines given in this unit? And the answer is 10,000 samples per second, and that is being driven in this case by the maximum source frequency. But we should still have analog anti-aliasing filters in case there is energy above 5000 Hz. Now let's take a segment of accelerometer data from our engine test in the previous slide, and let's convert that to a shock response spectrum, or SRS. Now the SRS is a time domain calculation, and in this case our maximum frequency of interest for analysis purposes will be 10,000 Hz. So what is the recommended minimum sample rate for this case? And again, the maximum frequency in the source energy is going to be 5000 Hz, or is at least expected to be 5000 Hz. So let's set our sample rate at 100,000 samples per second, and that is being driven by our maximum frequency of interest in this case. But once again, we still need to use analog anti-aliasing filters in case there is energy above 5000 Hz. Now we're going to turn our attention to the amplitude resolution. So the amplitude resolution for digitized data is measured in bits. And the amplitude resolution is 1 part in 2 to the exponent number of bits. So a 12-bit system has a resolution of 1 part in 4096. And here's an example that will help us to understand this principle. So let's consider a 12-bit system, and it's set up to measure a full-scale amplitude of 10 volts peak to peak, and that's from the sensor. The resolution in this case is 10 volts divided by 4096, and that's equal to 2.4 millivolts. And this example is shown in the next slide, along with 2 other cases. So again, our sensor, along with its signal conditioner, has a peak-to-peak amplitude of 10 volts. So if our data acquisition system is an 8-bit system, our voltage resolution will be 39.1 millivolts. If we have a 12-bit system, our voltage resolution is 2.4 millivolts. If we have a 16-bit system, then our voltage resolution is 0.15 millivolts. So a higher bit resolution yields a smaller voltage increment for the amplitude. Now, ground-based data acquisition systems usually have a fairly high bit resolution, so we usually do not need to worry too much about the amplitude resolution for a ground-based test. But flight telemetry systems have a limited bandwidth, and this requires that in some cases a lower bit resolution be used. Now consider the case of an accelerometer mounted on a launch vehicle. And this accelerometer must measure both high amplitude shock energy as well as low amplitude vibration energy. So the shock event will drive the range setting for the telemetry system. And as a consequence, the resulting vibration data may have a stair-step characteristic due to the low bit resolution. So let's continue with our previous example. The telemetry data is given in terms of bits, where the bits are in integer format. The user must then apply a scale factor to the bit values, and the scale factor might convert the bit values to volts or to some other engineering unit. The voltage resolution is proportional to the G level for an accelerometer. So let's consider a system where the accelerometer has a 10 volt peak-to-peak range and the accelerometer sensitivity is 10 Gs per volt. Now that's equivalent to 0.010 Gs per millivolt. The accelerometer signal is then applied or input to a 12-bit data acquisition system. So we have 2 to the 12th power equals 4096, and that will be the amplitude steps. We then take 10 volts and divide by 4096, and we have a 2.4 millivolt amplitude resolution. And we actually did this calculation before 2 slides ago. Now we take our 2.4 millivolt value for our amplitude step, we multiply by the accelerometer scale factor, which is 0.010 Gs per millivolt, and we have a 0.024 G amplitude bit resolution. The available amplitude levels are then shown in the last line in this slide, and any intermediate values or in-between values will either be truncated or rounded depending on how the data acquisition system is set up. Here's an exercise. Some actual flight telemetry data is given in file t_flight.txt, and this is flight accelerometer data. There are 2 columns, time in seconds, and the amplitude is in terms of bits. And this represents a transient event which occurred during the burnout of a solid upper stage motor for a launch vehicle. Now the amplitude resolution in this case is 0.2 G per bit. So let's convert the amplitude column to G units and plot the data. Here's a MATLAB script called signal_functions. So please go to your MATLAB workspace and type in this function name. Now this program performs post-processing on a time history signal, and the signal must have 2 columns, time in seconds and amplitude. And let's select choice number 1 for external ASCII file, and the file name is t_flight.txt. And next you'll see a list of menu options, and we're going to pick option number 4. This is multiply amplitude by scale factor. And our scale factor will be 0.2, and again this is needed in order to convert the bit value to a G value. Then for the next step, please use option 16 to view stats and plot the resulting time history. Now we started with a flight accelerometer time history that had time in seconds and the amplitude was represented in terms of bits. We've now converted the amplitude column to acceleration in G. So here is the resulting time history for this flight event. And this time history is given in the MATLAB file name signal_post, and that was the output file from the signal function program that we previously ran. The time history from the flight event in the previous slide appeared to be composed of several damped sinusoids. So let's determine what those underlying frequencies are. So in a previous unit, we ran program Fourier.m. This is a MATLAB script. And let's run this script again. So in this case, we're going to have a file that's preloaded into MATLAB, and this file is going to be signal_post. And this is the output file name from the signal_function program, where the original file was t_flight.txt. But now that we've converted the amplitude in bits to amplitude in G, our file is now called signal_post. Then we'll choose plot only, option number 1, mean removal yes, number 1, select window, rectangular, number 1, and then we see some descriptive statistics for our Fourier transform, and we note that the peak occurs at 313.63 Hertz. So here is the resulting Fourier magnitude for our flight accelerometer data. The x-axis is frequency in Hertz, and the y-axis is acceleration in G. And there are spectral peaks which occur at 70, 83, and 316 Hz. And these frequencies could represent, for example, some structural natural frequencies that were excited by the flight event. And we would need some further consideration to determine if that were so. For example, if we had some modal test data or some finite element results, then we could compare that with the flight data. Now we need to be a little bit careful about the spectral peak at 316 Hz, and it might represent the combined effect of several modal frequencies which are closely spaced in terms of their respective frequencies. And let's go ahead and run signal underscore functions one more time. In this case, we'll have an external ASCII file which will be ins.dat. And this is flight accelerometer data from an inertial navigation system. And the data is sampled at 100 samples per second. And let's use option 15 to plot the cubic spline with a sample rate of 500 samples per second. And here's the raw data from the inertial navigation system. And this is a time history, and the amplitude is unscaled, and we're not going to worry about what metric or what unit it might be. But the point of this data is that the data is fairly coarse, and that's due to two reasons. One, the limited sample rate, and also the limited amplitude bit resolution. Now here's the result of our cubic spline curve fit. So our x-axis is time in seconds, our y-axis is amplitude, and the blue curve is the original data, the raw data, from our INS system, and it was fairly coarse. Then the red curve is a smoother curve, and this is sampled at a sample rate which is 500 samples per second, which is 5 times that of the original data. So the red curve is much smoother, and it's a plausible representation of the actual event. But we still need to be somewhat cautious in how we use this tool. And this plot is the same as that shown in the previous slide, only in this case we've zoomed in on a segment of the plot in order to get a look at the details of the curve fit. Here's a summary of the scripts that we've run in this unit. The first is signal underscore functions.m, and we use this script for the t underscore flight.txt file. And in this case, we needed to convert the amplitude from units of bits to amplitude in terms of acceleration in g. Then as a review exercise, we ran script Fourier.m, and in this case we took the Fourier transform of the t underscore flight.txt data, where the data had been converted to acceleration in g. And then we identified several spectral frequencies which may have corresponded to structural natural frequencies excited by a flight event. Then we took a look at file ins.dat, and this was flight accelerometer data from an inertial navigation system. And we again used the signal underscore functions.m script, but this time we used the script to perform a cubic spline fit on the INS data. So I hope that you've enjoyed this unit, and you can use these MATLAB scripts as well as the rules of thumb that we established for setting sample rates for telemetry and data acquisition systems. Please contact me if you have any comments or questions. Thank you.